Hello everyone. Now we will see some properties of convergence in distribution. So what is convergence in distribution? Let us revise. So if I have a sequence of random variables xn, we say that xn converges to x in distribution or in law if the CDF of xn converges to CDF of x for every x in set of continuity points of fx. Okay, continuity points of the distribution function of the limiting random variable. Okay, this is important. So if it is not converging for some x at which there is a discontinuity, it is fine. Okay, so let us take a couple of examples. First, let us start with a simple example. Suppose xn is exponential random variable with mean 1 plus 1 by n. Okay, parameter is not 1 plus 1 by n, mean is 1 plus 1 by n. Then what do we know about CDF of xn? CDF of xn would become probability of xn less than or equal to x, which is 1 minus e raised to minus x upon the parameter. So the parameter is 1 plus 1 by n. Correct? So as n goes to infinity, what happens to this function? As n goes to infinity, 1 plus 1 by n would go to 1 and hence this would converge to 1 minus e raised to minus x. Okay. So we know that this is nothing but CDF of standard exponential distribution. Hence we say that xn converges to x in law where x is standard exponential. Okay. So this is an example of convergence in law. Let us take another small example. So suppose I have xn coming from normal distribution. Suppose xn follows normal 0 1 by n. Okay, so mean is 0, variance is 1 by n. Now what do you expect? Since variance is 1 by n, variance is decreasing. As n goes to infinity, correct? So we probably expect that this goes to a degenerate random variable, degenerate at 0. So let us try to check. What is CDF of xn? CDF of xn at any point x would be probability of xn being less than or equal to x, and we can use the usual trick of standardization. So this is same as probability of root n xn being less than or equal to root n x, so that we can use the standard normal CDF. Okay, so this is same as probability of z, standard normal random variable, being less than root n x. So this is CDF at root n x. Now what do we know about limit of this quantity? As n goes to infinity, if x is less than 0, then root n x will go to minus infinity if x is negative. Okay. Similarly, if x is positive, root n x will go to plus infinity, and if x is equal to 0, then root n x will be 0. Okay. So let us use these three things. As a result, what happens to limit n going to infinity of fn x is, if x is negative, phi of minus infinity is 0. So this goes to 0. It will go to 1 if x is positive, because phi of plus infinity is 1. and if x is 0, then I'm going to get phi at 0, and we know phi at 0 is half because the distribution is symmetric around 0. Okay, so this limit takes actually three possible values: 0, half, and then 1. Okay. However, we had mentioned that we are expecting that this converges to a random variable which is degenerate at 0. What is CDF for that? CDF for that is 0 if x is less than 0 and 1 if x is greater than or equal to 0. Now, are these two limits equal? Technically, they are not equal because at x equal to 0, the values are different. At x equal to 0, I have half here, whereas here at x equal to 0, I have 1. But I can still say that fxn x converges to fxx for every x in set of continuity points of fx, because we know that this distribution function is discontinuous at 0. At 0 there is a jump. But except for 0, everywhere else it is continuous, and this matches with this everywhere else. Only at 0 it doesn't match. Okay. Hence, we can still say that xn converges to x in law, where x is a random variable degenerate at 0, because except for 0, everywhere else fxn x converges to fxx. Okay. This is an example where you are not getting entire, in the exponential case, our fxn actually converge to fx for every x. Whereas here we have an example where there is one point of discontinuity at which the limit doesn't match, but still we are okay with it. Okay. So if xn converges to x in law and if xn also converges to y in law, then we cannot say that x is equal to y. Okay, these need not be equal. We can only say that distribution of x and distribution of y matches at the continuity points. Okay, we can't say that they are almost surely equal. We used to do that for probability convergence and almost sure convergence. However, convergence in distribution is much weaker, and hence we cannot guarantee that x is equal to y. Okay. So this is important. We shouldn't forget this. However, some of the results do get carried over to convergence in law. One such result is the invariance under continuous transformation. Okay. So if xn converges to x in law and if g is a continuous function, then gxn converges to gx in law. Okay, this is an important result and it has lot of applications, especially when we are doing inference, asymptotic inference. Okay, you might have studied this already in asymptotic inference. Let me state the result. It is also known as delta method. So delta method gives me a way of constructing more and more estimators. So suppose Tn is an estimator of mu. Tn is an estimator of mu and it's a good estimator. Good in the sense it is consistent and asymptotically normal. Then we know that root n times Tn minus mu converges in law to x, which is say normal 0 sigma square. Okay. Then if g is a differentiable function, if g is a differentiable function with g prime mu not equal to 0, then root n times gtn minus g mu converges in law to normal 0 g prime mu whole square sigma square. Okay, So a differentiable function of an estimator is also consistent and asymptotically normal for the corresponding function of the parameter. So this is a very important result. It gives us, it opens up the possibility of many estimators being consistent and asymptotically normal. Now you might have started thinking that normally expectation of GTN is not same as G of expected TN. We know that. Unless things are linear, expectation cannot be taken inside the function. However, here it is happening. So why it is happening? It is something like Taylor's series. So you do have other terms contributing when you expand. However, those terms have, in the limit, those terms have no role. They go to 0. And hence finally we get something like expectation of gx is g of ex. But remember, it is asymptotically true. It is not true in the exact sense. Okay. Okay, so this is important result. Couple of other results that are important is, we know that convergence in probability is stronger. Convergence in probability implies convergence in law. But are there any situations where reverse happens? Yes. So if xn converges to x in law and if x is degenerate, okay, if x is degenerate, then xn will converge to x in probability also. So the reverse implication holds if the limiting random variable is degenerate. And as a result of this implication, we can have algebra of sequences also. So if xn converges to x in law and yn converges to c in law, means yn converges to a degenerate random variable, so c is some constant, then xn plus yn and xn minus yn converge in law to x plus or minus y. So y here actually means c, so x plus or minus c. Then xn into yn converges in law to x into c. xn by yn converges in law to x by c, provided these are defined. Okay, so provided c is not 0 and yn is not 0. Okay, and of course if c is 0, then I would have x and yn converging to 0 in law, and because of the result that we stated here just now, this would also become convergence in probability if c is 0. Okay, so because the limiting random variable becomes degenerate, and hence convergence in law is equivalent to convergence in probability. Okay, so this is also an important result. Where we are going to need all these things? We are going to need convergence in law mainly while proving CLT, okay, the central limit theorem. So in CLT again we are going to need one more important result. If xn is a sequence of random variables and if phi n is a corresponding sequence of characteristic functions, means phi n is a characteristic function of xn, then convergence of characteristic functions is equivalent to convergence of the random variables in law. So phi n t converges to phi t for every t in R if and only if xn converges to x in law where phi t is characteristic function of x. Okay, so if you have a sequence of characteristic function and if you can prove that it converges to some characteristic function of some random variable x, then you can say that xn converges to x in law, and the reverse thing is also true. This is going to be used quite a lot in central limit theorem. We will try to prove that the sequence of characteristic functions converges to the characteristic function of standard normal random variable, and hence we would conclude convergence in law to normal random variable. Okay, so this is an important result. Now I have some small homework for you. It's quite easy. We saw in the beginning couple of examples where we took limit over CDF and checked the limiting distribution function. You have to do something similar, but now we are trying to prove that not everything goes to normal. Okay, so suppose you have x1, x2, xn, IID, uniform 0 theta, and x ordered n is your order statistic, so it is maximum of x1, x2, xn. We know that x ordered n is an estimator of theta. What can I say about theta minus x ordered n? Now as you can see, because each of them is coming from uniform 0 theta, theta minus x ordered n is always going to be greater than or equal to 0. Correct? Hence, in the limit also, it cannot probably have normal distribution, because normal distribution means it has to take positive as well as negative values. Okay. So, usual thing like root n theta minus xn bar, theta minus x ordered n doesn't work. What you have to prove is, you have to find the distribution of n times theta minus x ordered n. Okay, this is your homework. Try to find what is the limiting distribution of n times theta minus x ordered n. Okay, the answer is actually exponential. So try to check if you can do this. So that's all we would need about convergence in law. So let us stop here. Thank you.